Hi, friends. This is John. I'm passionate about developing regenerative agriculture systems that improve soil health, produce crops that are completely resistant to diseases and insects, and produce food of such an exceptional quality that we can have a legitimate conversation about growing food as medicine. I've been fortunate to meet many people with incredible knowledge and information about soil and plant systems. However, much of this knowledge and information is scattered all over the place. I founded Advancing Eco-Agriculture in 2006 to bring this knowledge together in a more coherent fashion and incorporate it into products and growing systems that growers can easily put into practice. It's my personal mission to have these regenerative agriculture systems become the mainstream globally, the status quo against which all other growing systems are compared. To achieve this goal, I want to share the knowledge that we have learned in the last decade and make it available to everyone. If you have any questions, suggestions, comments, or topics that you would like for me to discuss, please connect on social media or email me, john@regenerativeagriculturepodcast.com. Be sure to sign up for our email list at regenerativeagriculturepodcast.com. Hope you enjoy, and thank you for listening.
How can we grow food humanely and sustainably, regenerate our soils, and reverse climate change? Learn practical and cutting-edge solutions to these issues and more at the 40th Annual EcoFarm Conference, January 22nd through the 25th in Pacific Grove, California. EcoFarm is an essential networking and educational hub for ecologically minded farmers, ranchers, and all who work to support their success in growing a healthy food system and world. There are over 70 workshops, keynote speakers, farm tours, an exhibitor marketplace, seed swaps, live entertainment, and organic culinary fare. If you care about sustainable farming and our food system, you don't want to miss EcoFarm. This event is a benefit for the Ecological Farming Association. To learn more and to register, visit eco-farm.org. ecofarm.org.
Hi, friends. I'm delighted to introduce Walter Jehne. Walter and I have been trying to connect for some time. We live in a very interesting world from a climatic perspective. All of us get to experience and observe how the climate is shifting and changing on our own farms and on our own operations. And Walter has developed a very unique perspective on the impact that we as farmers can have on the climate and how we can shift management of our own farms to improve carbon sequestration and to do all these various things. We've just in the last week had the most recent IPCC report release, which describes the impact that regenerative agriculture can have on improving the climate. But I think an important element that Walter adds is one that is usually missed. The reason we want and need carbon sequestration and the impact that we can have as growers, that the point is not to sequester carbon purely to remove carbon dioxide from the air, but instead to change the hydrological landscape, to change the way water moves in the environment. And I know this is a very important piece for all of us because obviously water is foundational to how we manage our farms and improving the yields of our farming landscapes. Walter, I'm very excited to have you here. What led you to start looking at the impacts of water on atmospheric temperatures and considering a different narrative rather than CO2 as the primary greenhouse gas?
Right. Thank you very much, John, and thank you, everybody, and for having me all the way from down under Australia, and delighted to be here. But look, your question very much to the point, why consider water? Well, I mean, when I was first studying, at university and stuff in the 60s, Climatology 101 makes a very simple, absolute point, undeniable. Water governs 95% of the heat dynamics of the blue planet and has done for the last 4.2 billion years. So really, it's a foundational principle of atmospheric physics and the Earth's climate. This is before, of course, we got captured into the CO2 greenhouse component, which I must stress is absolutely real. It's absolutely real, but it represents less than 4% of the heat dynamics of the blue planet. Okay, so nature has, in a sense, evolved a hydrological balance that has both warmed the planet and made it 33 degrees centigrade warmer than it would be if it was just an inert physical body in space in this part of the solar system. Okay, so the natural greenhouse effect due to water vapor makes it 33 degrees warmer, but it's also our disturbance of that 95% of the heat dynamic process that has now caused the abnormal warming in the last 250 odd years, which of course was picked up then by Charles Keeling in 1958 when he sort of said, hey, here's CO2 going up, but that CO2 rise, people make the mistake, they see that as that must be the cause. No, that is a symptom. Okay, that CO2 rise is a symptom of our disturbance of the biosystem from our excess oxidation of carbon from the biosystem. It's simply a symptom, but the actual thing that's driving the climate change is the effect of that land degradation on the hydrological dynamics of the planet. And so the challenge isn't just to draw down the carbon dioxide or see it as a pollutant, which is just silly. The point is it's our resource. That's the building block that we need to take to rebuild our landscape, our soils, so that we rebuild the hydrology that we've disturbed, and in rebuilding that hydrology, restabilize the climate, cool the climate safely and naturally in the next 10 years. Because if we leave it longer, it's very, very serious, dangerous, and damaging.
As farmers and growers, we love to have higher CO2 because we get better plant growth and we get higher yields. So I've been particularly intrigued by the conversation that you have led and your contributions to the dialogue. One of the questions that I have is we do see these climate variabilities and these intense climate events across the countryside. How can we stabilize the climate and how can we cool the climate without reducing CO2?
Okay, important here that we sort of clarify that, right? We will have to reduce CO2 for the simple reason that we have to rebuild the Earth's soil carbon sponge. And that's the one simple message that this is all about, regenerating the Earth's soil carbon sponge, because that's where the bridge between carbon management and hydrology management really hits the ground. That's our unique point of agency. That's what we've destroyed. We've destroyed the soil carbon sponge. And in that process, we put CO2 in the atmosphere. We've also then aridified and reduced the amount of water available. Just not picking you up, but just clarifying. You say you like actually CO2 because absolutely you get a fertilizer effect, but only, John, if you have soil water.
Exactly.
For most of the landscapes around this world and your Central Valley in California, they'll tell you that as well. Without water, whatever CO2 is up there is no use whatsoever, right?
Absolutely.
So basically, without water, there is no life, and therefore it's the sponge. And so what we're really saying is that here is a symptom. The CO2 has gone up because we've oxidized, degraded the landscape. We've got to take that CO2 as a resource, as the actual cement to rebuild the healthy soil structures, to rebuild the cathedrals of voids and surfaces in healthy soils, because it's the voids and the surfaces in soil is where the water is able to be infiltrated, retained, and that's where productivity, that's where resilience comes from, right? The actual cathedrals of voids, the space in those healthy soil structures that we have to rebuild. As far as the dangerous hydrological climate extremes and variability that we're facing, and this is again fundamental, that's absolutely correct. We're not going to die from CO2. Submariners die when CO2 in their subs gets to 10,000 parts per million. It's 400 parts per million now. When you and I breathe out, we breathe out air that's got 1,000 parts per million CO2. So we're not going to die from CO2, but we are going to die if we aridify and don't have the water for life or for the planet and the food that we need to produce. So it's a sponge, and really CO2 needs to be seen as our resource and building block to rebuild healthy soil structures. Okay, so that CO2 is a resource to build the sponge, and then the point of the sponge is that is a thing that's critical to buffer the extremes, right? It's in a sense the sponge that allows us to infiltrate water into soil, to minimize the flood peaks, to minimize the erosion, storm damage, and basically it's also the source where we can sustain the longevity of green growth. So when there are dry periods, it's only the sponge and the water in our sponges and our in-soil reservoirs that allow life to extend over those dry periods. So with climate change, we're not just warm the planet 3 watts per square meter, or roughly 1% of incident solar radiation extra that we're retaining, but we've triggered this extreme variation, dangerous extremes. They're all hydrological, and really the sponge is the point of agency in nature, and now our only point of agency to rebuffer and stabilize these extremes. It's extremes that are going to actually destroy us and destroy biosystems and kill people, because whether they are hurricanes, whether they're floods, whether they're erosion, whether they're aridification, droughts, wildfires, it's these extremes, and they're all hydrological, and they're all prevented by buffering through the sponge.
One of the considerations for the soil carbon sponge that I've spoken of in the past is not only the capacity to store water, which I think is obviously very important, but also the capacity to deliver water to plants when they need it. It's not just soil water holding capacity, it's also water release capacity.
Absolutely, John. And actually, let's take that one extension. It's the longevity of green growth that governs the whole health of the biosystem, our food production. You see, it's a capacity to sustain over time enough water supply from the soil to maintain that crop finishing, that pasture growing. If we have a sponge and we get to say 1 inch of rain, then we can say that water infiltrates and will be made available slowly over just say 100 days. If we concrete that catchment and degrade that sponge, and we have a hard compacted soil, it basically runs out of water after 5 to 10 days or less. It just runs off, erodes. So we have, in a sense, 1,000% increase in productivity, a tenfold increase in longevity of green growth from maintaining a sponge. And I was a scientist involved with the Green Revolution, I mean, more from a nutrition point of view. But at those days, or anything in the Green Revolution, if we could get a 30% growth response, we thought that was a world-shattering good news story. But here we are. The sponge will give you 1,000%, a tenfold longevity of green. And in a sense, your community has been doing this wonderfully for centuries. But that's the message we've got to get across wider. We've got to build resilience, longevity, healthy biosystems, not just short-term, fast growth dependent on fertilizer inputs, irrigation, and these inputs, right?
Yes, I believe the general regenerative and biological agriculture community has certainly on some level understood the importance of developing the soil carbon sponge and building organic matter and improving soil water holding capacity, etc. But I think something you can contribute to the conversation that is not well understood is how does that improvement in soil water holding capacity then contribute to a stable climate and to a cooler climate? So from an atmospheric perspective, what is different today than what existed, let's say, 100 years ago or 50 years ago?
Okay. And this is in a sense where we step into, the atmospheric physics or the atmospheric heat dynamics. And these are they're totally natural, totally proven in nature, but new concepts to a lot of the climate scientists who sit in front of computer screens and model away. Okay, every time a tree or plant transpires, longevity of green, right? and it takes water from the soil and turns it from a liquid into a gas, water vapor, that transpires. And to do that, every gram of water needs 590 calories of heat energy to make that transformation from liquid to gas, called the latent heat of vaporization. And that heat, of course, comes from the surface soil and the surface environment. And so every gram, every cubic centimeter of water that's transpired cools the surface 590 calories of heat energy. And of course, you understand there's vast quantities of transpiration taking water up into the air over long periods of time. So this is a massive, natural, safe cooling effect. But we, by degrading our landscape, in a sense, concreting catchments so the water isn't in the soil, limiting the longevity of green growth, we're limiting that natural air conditioning cooling effect of the planet. Okay, and so immediately, simply shortening productive green growth results in a warmer surface because we don't have this latent heat transpiration cooling. Globally, some 25% of the incident solar radiation coming from the sun is naturally transferred from the surface back up into the atmosphere through these transpirational latent heat fluxes. So globally, it's 25, a quarter of the global cooling balance is driven by green transpiration. And so the message is simple. If we increased the quantity and the longevity of green transpiration by some 4 to 5%, we would offset the abnormal warming that we have induced today.
That's not a significant amount. So how much would we be able to cool the planet? What temperature reduction would we be able to observe if we increased that transpiration?
Okay, so yes, so that would cool the planet, basically that 1%, the 3 watts per square meter that is abnormally warm. There's no danger that we would overcool the planet because, as in nature, the planet is heat buffered and regulated, right? If we cooled it too much, transpiration and photosynthesis would slow down and would self-regulate, right? So there's no danger of doing this to turn an ice age on, none at all, because photosynthesis would slow down, transpiration would slow down, right? And we'd be still back in natural homeostasis. But to offset the abnormal warming, the 3 watts per square meter abnormal warming, we could simply increase transpiration by 4 to 5%, and that would be the offset. Now, let's caution here, it's not quite that simple. I mean, the facts are there, the maths are there, but the natural hydrological process is a bit more complicated, so it's not just one single magic bullet that we're proposing, but we're just trying to illustrate this is part of that whole dynamic. There's another part, again, it gets not complicated, but there's more parts to it. For example, clouds, right? High albedo reflective clouds. Again, they reflect up to a third of the incident solar radiation back out to space, so that heat doesn't even get to the Earth. And so a 2% increase in cloudiness, in a cloud density and reflectance, would again offset the abnormal warming that we have induced today. Okay, and so that's again doable, but only if we have the sponge, because without the sponge, we don't have the water to transpire into the air to form clouds to drive these cooling processes. So if we concrete the catchment, we end up like Mars, and we don't have any of these cooling capabilities.
Walter, it's my understanding that to really have the cooling capabilities and to cool the entire planet down on a global landscape scale, what I've understood from our conversations in the past is that we need three things. One is we need the carbon sponge, we need the holding capacity to hold the water. And then two, we need the capacity to change the way water behaves in the atmosphere. And water in the atmosphere, as I understand it, behaves differently today from what it has in the past because of the way we've impacted aerosols and other things in the atmosphere. Can you tell us a little bit about that?
Of course, John. And again, thank you. This is a very next chapter in a way. And again, it's elegantly balanced, and you really have to be on your knees to nature. But again, let's explain it, right? Basically, nature has governed the temperature balance of this planet through evolving two very sophisticated opposing processes that either warm the planet or cool the planet. Okay, so we've talked about the water vapor going up from the trees, which cools the surface. But that water, when it then goes into the atmosphere, condenses and releases that energy, most of which, or a lot of which, transmits back out to space, but then forms haze microdroplets. Okay, and we see these as mists and hazes in the air. And of course, we see them because they are microdroplets. We can't see water vapor, but we can see droplets. And of course, the hazes are billions, trillions of these microdroplets. And to form a microdroplet, water, in a sense, has to condense onto an aerosol particle. And in nature, and this is James Lovelock work from the 1960s, in nature, nature produces a lot of these aerosols from plants and vegetation, the dimethyl sulfide from marine algae, the isoprenes from forests, the pinene, the terpenes, again from forests. So that nature is producing a lot of these aerosols, and they actually create the hazes, and they actually provide a natural warming effect in the atmosphere. But what's happened is we have massively increased the amount of these aerosols that are now in the atmosphere abnormally. Let's go through some of them. We have created 5 billion hectares of man-made desert and wasteland on this planet. There's only 14 billion hectares of land in total, so 40% of the land surface is now desert and wasteland, which produces some 4 to 5 billion tons of clay dust particles entering the air every year, and these are acting as haze, particulate, and so the amount of haze has increased enormously. Every year we burn 400 million hectares of forest and some 2 billion hectares of grassland on this planet. And of course, the carbon particulates from that fire is going into the atmosphere and again increasing hazes. Every year we burn 8 billion tons of fossil fuels, and again a whole lot of carbon particulates and polyaromatic hydrocarbons entering the air. So we have created a massive increase in this aerosol release, and as a consequence, the level and density of these humid hazes and their warming effect. We have a pollutant brown haze that now stretches from Cairo to Beijing, and in a sense, people are suffering under that with all sorts of pollutant effects and also heat effects, because these humid hazes heat that area. For example, in the Middle East, the Persian Gulf, now in summer, it's 50 degrees centigrade temperature, 95% relative humidities, well exceeding the capacity for mammals, including humans, to survive, because we can't perspire, we can't cool ourselves. So this is this dangerous humid heat, health impact. So we are really cooking ourselves, right? Saunaing ourselves. So that's the heating component. And then nature, to offset that and to balance that, has actually evolved another even more exquisite process. And these are the hygroscopic precipitation nuclei. Now, they're scientific words, but what it is, nature has, again, molecules in the air which absorb and coalesce about 1 million of these haze droplets to make a cloud droplet. Okay, and so nature says, right, I can regulate hazes, but I can also coalesce hazes into dense high albedo clouds. And as we've talked about, these clouds reflect sunlight and actually cool the planet. So through this simple matter of coalescing hazes into clouds, nature can switch it from a warming to a cooling process. And it's through this balance of these microbial hygroscopic nuclei that nature has regulated the temperature of the atmosphere. But if I just add these three components that cause this hygroscopic removal of hazes into cooling clouds. and they are ice crystals. And of course, they're critically important at high altitudes, high latitudes, and cold fronts. And basically, they're forming those clouds. Over the oceans, we've got salt, sodium chloride, which creates most of the clouds over the oceans. And of course, we use salts like silver iodide in all our research on cloud seeding, which my institute was involved with very significantly in the 60s and 70s. But the most important precipitation nuclei that is produced in nature and drives over half of the rainfall and cloud formation, particularly in tropics and inland areas, are bacteria. Bacteria produced in the stomatal cavity of certain trees, which then go up into the air as part of the transpiration stream, actually nucleate these hazes to form dense clouds and then rain, and basically drive the whole hydrological cycle. Okay, because it's one thing to put water vapor or hazes into the air, but of course nature has had to evolve a way to bring it back down through clouds and then rain, because only then has it got regulation. So it's these bacterial, hygroscopic bacterial precipitation nuclei that become fundamental in that regulation. And again, they're produced by certain forests. And of course, us destroying those forests, again, has a massive effect. And we've got lots and lots of hard evidence whereby forest destruction has now crashed rainfalls in regions, even though there's still other vegetation there. But remove the forest, you lose the rainfall, you aridify those regions. So rebuilding this balance between haze nuclei or haze formation through aerosols and then the removal via these precipitation nuclei is a fundamental balance that we have to restore.
Walter, what is missing to restoring that rebalance? We're obviously we are. It seems to me that we are producing a tremendous amount of hazes in the environment because, as you described, we experience many days now where we have very warm temperatures and 95% humidity here in the Midwest. That didn't used to be the case, even in my very short memory.
Right.
It was very unusual to have a large number of days during the summer with 95% humidity. It would happen occasionally,
Yep.
but not that frequently.
Okay, and this is wonderful. This is getting to the practicality. Okay, so we want to reduce the hazes, and here are the really practical, very rapid sort of ways that we can and must do this, right? The first thing, of course, is you're already doing it in a way. First of all, we maintain soil cover, right? We maintain vegetation, protective cover on soil as nature had, because it's basically when we have bare, exposed soil to heat, to wind, that we get dust, and there's 4 billion tons of dust aerosols that we can then reduce on the planet. Right? Obviously, we can't reduce it everywhere. The deserts, for the time being, are deserts, but the more ground cover, the more ground insulation, yes, we can do that practically everywhere. Secondly, we can stop some of these fires, right? We have these massive fires. They put up more carbon dioxide into the air than our burning of fossil fuels, but we've never accounted for them because we've deemed them to be Mother Nature's problem, right? Well, it's wrong, because it's us that regulates fires in how we manage our forests and landscapes and manage this biodegradation of the fuel in the fires. And so if we can limit these wildfires, we can again massively limit the carbon particulates in the air. Obviously, we've got to keep on trying to reduce fossil fuel use, and that goes without saying. And of course, the polyaromatic hydrocarbons and things like that coming from there. So we've got a massive capacity to reduce the hazes by limiting the aerosols that create them. On the other side of the equation, yes, we can't change ice crystal formation readily, and as it gets warmer, there's going to be less of them. So be careful. We are triggering aridification, right? Because there's less ice nuclei. We can play around with putting salts in the air, as we do with cloud seeding, silver iodide, but again, very expensive, and it's a bit hubristic in a way, but also very limited in scale. But what we can do is we can say, okay, how do we restore these natural forests that are producing up to 1 billion tons of bacteria, protoplasm content that's going into the air every year, acting as these hygroscopic precipitation nuclei. If we look at the scale on that, we used to have 8 billion hectares of primary forest on this planet 10,000 years ago. We have cut 6.3 billion hectares of that forest. Some of it is regenerated, so now we've got 3.5 billion hectares of forest. Basically, we have massively, massively disturbed and reduced the amount of these hygroscopic precipitation nuclei that were naturally produced by forest. And of course, in that, we've changed the cloud formation capacity, but more seriously, we've changed the rainfall induction, because what happens is these hygroscopic precipitation nuclei form first clouds, but then they continue to coalesce cloud droplets into rain droplets that are big enough and heavy enough. And over half of the rainfall on this planet is driven by these hygroscopic bacterial nuclei, effectively in a symbiotic process. We all know that trees and plants need rain, but now the question is nature, rain needs trees.
Walter, how large a forest or how many trees are needed to release these bacterial nucleations into the atmosphere and produce rainfall? From a very practical level, if we consider the possibilities of increasing or moderating rainfall in the Midwest, let's say, for us as a collective group of farmers in the Midwest, how much forest and how many trees need to be present to moderate rainfall in the local environment?
Well, John, you win the prize because absolutely. You asked the really important question. And the honest answer is I don't have a precise answer because we haven't ever given ourselves the space and time to research and to get that information, right? Basically, we have enormous amount of detail on this thing. These bacteria, they're called Aerobacter orogenes, were described by Louis Pasteur in the 1870s in some of his fundamental groundbreaking work. He then went sampling in the air, climbed to the top of Mount Blanc, the highest mountain in Europe, opened a jar, collected the air, looked at the bacteria in it. They're everywhere. But your critical question of, okay, what forest, what species, what age, what density, what area is needed to have what rainfall effect, I'm afraid we need that data. We can get that data, but no, we don't have that data because, quite frankly, we have, through this discussion we're having and what we're doing, we have just opened a door into a whole new paradigm of, the hydrological ecology of the atmosphere is driven by microbes and vegetation. Okay, and that's earth-shattering because everybody said, hey, no, the atmosphere is all about atmospheric physics, dead stuff. And we're saying, no, this microbiology, it drives so much of the climate. So look, it's frontier stuff. I don't have a precise answer, but I do have an answer, right? So it's always that paradox. As I said, Louis Pasteur, 1870, defined this. Charles Darwin and Hooker, who was the president of the Royal Society in Britain, basically said we need to do an experiment in 1880, right? So this is 140 years ago. And on Ascension Island in the middle of the Atlantic Ocean, in St. Helena, another little island, basically the British had a naval outpost, reef supply depot, had put goats on the island. You know exactly what happened to the vegetation on those islands because of the goats. And they sort of said, we've got to revegetate these islands. And they had two mountains on Ascension Island. One they call Bald Mountain, and the other they call Green Mountain. Green Mountain, of course, is where they revegetated forest 140 years ago. And Green Mountain now gets 20% more rainfall than Bald Mountain. They're 20 kilometers apart. Not 20, actually. That wouldn't be that big. 10 kilometers apart. Okay, so here we are. There's plenty of evidence, direct experimental reality that yes, restoring forests create rain. But
Yes, and there's a lot of, as you described, a lot of anecdotal evidence on smaller scales. I'm thinking of Las Gaviotas in Colombia and Other stories of regenerative farms that have significantly changed rainfall in the local environment with relatively small amounts of trees, a few square kilometers or less, in many cases, quite a bit less.
Okay, but can I pull you up there? Now, please, please don't say this is not hard. This is reality, right? That's nature. That's reality. So don't let anyone bluff you that that isn't evidence. Nothing is more solid as evidence as nature. Okay, so just because it's not in somebody's computer model, you know, don't ever doubt nature. Back nature, because that is reality. That is what nature's doing. There, that's where the answers are. So wonderful, because what you've just said there, John, is actually the proof. And don't doubt yourself, because that's really where evidence is. It's not in somebody's assumptions and computer model on a yeah in an illusion that they're living in. And that's in a sense the problem we've got, because the conventional science says not proven, not proven. Well, no, sorry, reality has been proven. Reality is reality.
Yeah, I think just we have enough experience, and I would say of the collective we as a human species, we have enough experience that even while the evidence may not yet all have been quantified and published in the peer-reviewed literature, we are in a situation where we need to take the experience that we already have and apply it. We can't afford to take another 10 to 20 years to first quantify it and first validate it. We need to begin immediately with what we already know.
And we need to answer to say it is validated. There is nature. You're standing in it. You don't need some computer model to guess at it, right? And so, yeah, I'm 300% behind you, backing you. And I mean, obviously, if you have people who have documented, yes, we have reforested this area, we have had these hydrological effects, that is reality and that is the evidence. So, I mean, I'm just so passionate about backing reality and backing those innovators in the field, because that's the front line of knowledge, understanding, and actually saving this planet.
So I think for all of us as growers and farmers around the countryside, we need to begin thinking, as Walter has described, about regenerating the hydrological cycle. That is, of course, covering our soils, making sure that we have a longer green period with longer transpiration, but then also making sure that we have an adequate population of trees in the local landscape, in the local environment. I believe that would significantly change the rainfall patterns throughout much of the US Midwest and the Great Plains region if we were able to do that.
Absolutely. And in a sense, let's go further, because I work in Australia in arid areas. Of course, Australia is a pretty dry place. And first message is, yes, you've got to put these trees back, but they are actually beneficial, because they stop the desiccation, right? The evaporative desiccation, the wind speed, the scouring, which is where you're losing at the moment 50, 60% of the moisture you've got. Okay, so they're actually saving moisture. Don't let anyone tell you the trees take moisture away, because they save more moisture. More than that, they create much, much more palatable vegetation under them. So rather than having a pasture, for example, that is sclerenchyma, effectively cardboard, you've got palatable, nutritious pasture. So while it might only be 80%, 90% of the dry weight, it's got 400% palatability, feed conversion value. The trees are pumping up nutrients from depth, from soil horizons that the pastures can't get nutrient from, and they're bringing those nutrients into the surface soil cycles, increasing the biofertility of those pastures. So, I mean, these trees integrated, what we call shelter woods, are massively important, particularly in dry areas and as regions desiccate, and they are desiccating. So really, that's one of our frontline lifeboats for regeneration, okay? Integrating, and it's only need 50 trees per hectare, 20, 30 trees per acre, are really powerful in building resilience, driving hydrology improvements, building nutritional improvements, and actually giving you a lifeboat that can survive.
Walter, I was going to ask you how you are using trees in Australia. Are they being planted in shelter belts? Are they being scattered across the landscape? What do you find to be the most effective?
Right. Okay. Very important question. Thank you again, John. Okay. Basically, we have got now recognition globally, and people are talking about let's plant 1 billion trees and, give them 100 marks for aspirations and 5 marks for reality, right? Because planting a tree, unless it's got water, unless it's got the right soil environment, the probability it's going to be dead within 3 weeks, 4 weeks, right? And so that's the point. We've got to rebuild the sponge, we've got to rebuild the hydrology, because only then will a planted tree survive. But let's flip it around. If we rebuild the sponge and the hydrology, then mostly trees will naturally regenerate from seed from adjacent areas. So we can even avoid having to plant them. Trees will naturally reseed. If not, we can plant them from seed. So yes, we can regenerate vast areas of degraded, arid areas, not by planting trees, but just by rebuilding the sponges we've discussed, and then allowing natural successional regeneration of trees and grasses and shrubs to move into that area. If there's water there, life will follow, sure as eggs. Okay, no question. So that becomes the issue. Okay, how do we not just look at where we are above the surface and say, hey, we want this tree because that's what we can see. It's actually respecting down under what's in the soils, the hydrology, the nutrition, the microbial diversity, because once we have that, trees come automatically.
I think you make a very important point about trees coming automatically. Of course, in order for that to happen, that means that we cannot have sterile fence rows. It means we cannot have sterile borders between our fields, and we need to discontinue this ideal of having a completely clean field and clean field borders constantly being sprayed with herbicides.
Totally, John. And in a sense, in Australia, because we're a bit drier, we're going to a whole new paradigm for agriculture. We've got a big project with the Australian Academy of Science. It'll be middle of next year. How do we redesign agriculture for the future? And no, we've got concepts like nomadism, right? We've got to stop. I mean, we've imprisoned ourselves in the 19th, 20th century in these fence lines, right? So we have 4 pegs. This is our land. We put fences up and we try to overexploit that land till we die. We mostly will die if we stay that. But no, we've got to change that. We've got to get this whole concept of fences may have to go, where we have to say we have to be nomadic. Not that we actually individual move, but this nomadism, right? This new concept of agriculture where we opportunistically pasture crop where the seasons are. So with us, we're going right back to the wisdom of First Nations people. They've worked in the ecology of these systems, and we have to respect and then look at how do we apply that wisdom, particularly in an aridifying climate like Australia. But I agree, the idea of fence lines and spraying and killing, no, we've got to foster life. We've got to foster diversity and flexibility.
Walter, this has been a fascinating conversation. I know that you're a wealth of knowledge, and we could continue to have a delightful discussion for hours. But I want to be considerate of your time and our listeners' time as well. I'd like to ask one final question. In addition to all the pieces we've spoken about, what is an additional highlight or very important point that you think growers and farmers need to be aware of in managing this in the landscape?
Okay, simple take home messages, simple, yeah, the sponge, the sponge, the sponge, right? Just take the carbon and build the sponge. And of course, it's as simple as maximizing photosynthesis, just maximizing plant growth, as best you can, minimizing oxidative inputs, the excessive cultivation, the excess fertilizer, the biocides, the bare fallows, and then just understanding that organic debris is turned into humates and glomalin by soil microbes. And so if we just do that, maximize photosynthesis, minimize that destructive effect, let nature and microbes build that soil carbon sponge for us. The other key point, and we might have a future discussion on this, is really the nutritional integrity of the food we're growing. Depends again on the sponge and the nutrient availability on all those soil surfaces created in the sponge. We've massively compromised the nutritional integrity of the food we now eat, and our preventative health has crashed because of that. We have got exponential increases in all sorts of diet-induced diseases, totally unsustainable. And so down the track, it will be actually consumers demanding healthy food from healthy soils to keep people healthy. And in a sense, that's the forefront for the paradigm change, the tipping point, and actually our only way to feed and look after and maintain stable communities into the future.
Thank you, Walter. Excellent closing comments. And I will actually build on your point about the importance of the sponge as you described it. You'll hear me speaking much more in the future about soil compaction. It is impossible to build a deep soil carbon sponge when you are farming only 4 inches deep. I believe compaction is a significantly underestimated challenge in our production agriculture across the Midwest and across the country in North America. So you'll hear me speaking much more about that in the future. Walter, thank you so much for sharing your wisdom and your knowledge. And I look forward to having more conversations with you in the future. Thank you for being here.
Thank you very much, John. Thank you. And goodbye to everybody. And yes, thank you.
The team at AEA and I are dedicated to bringing this show to you because we believe that knowledge and information is the foundation of successful regenerative systems. At AEA, we believe that growing better quality food and making more money from your crops is possible. And since 2006, we've worked with leading professional growers to help them do just that. At AEA, we don't guess, we test, we analyze, and we provide recommendations based on scientific data, knowledge, and experience. We've developed products that are uniquely positioned to help growers make more money with regenerative agriculture. If you are a professional grower who believes in testing instead of guessing, someone who believes in a better, more regenerative way to grow, visit advancingecoag.com and contact us to see if AEA is right for you. Thank you for listening, and we look forward to working with you.